Good day everyone. Today, our group will present our integrated design project titled Cumene Production Plant Design. This project integrates concept from principle of chemical engineering and chemical engineering fluid mechanics to design an efficient process for producing cumene. So, what exactly is cumene? Cumene, also known as isopropylbenzene, is a colorless and flammable organic compound with a gasoline-like odor. It is mainly used as an intermediate for producing phenol and acetone, which are important chemicals used in plastics, resin, and industrial materials. Cumene is produced through an alkylation reaction between benzene and propylene in the presence of a catalyst.
My name is Muhammad Shahin Zikri, and now I'm going to present about the introduction of principle of chemical engineering. So, the production of cumene demonstrates important concept in principle of chemical engineering. To produce cumene, the process involves key engineering principles such as chemical reaction in catalytic reactors, fluid flow, heat transfer, and separation processes. After the reaction, distillation is used to separate cumene from unreacted material and byproducts such as diisopropylbenzene. Recycled streams are also used to improve raw material efficiency. In this project, mass and energy balance are applied to two main unit operations: the alkylation reactor, reactive unit, and the distillation column, non-reactive unit, to determine the flow rates and composition required for efficient cumene production.
Hi, I'm Cumene, and I'll be talking about the introduction to fluid mechanics. For the introduction, our design process focuses on the behavior of the fluids, both at rest and in motion. Within the Tokyo the process framework, we apply fluid statics to determine the pressure requirement for our storage vessels, and also fluid dynamics to calculate the flow rates of the propylene and benzene. A primary technical focus is managing the pressure drop across our system by calculating the friction factors and Reynolds numbers. We ensure that our pumps are sized correctly to overcome the energy losses, maintaining steady efficient flow through the reactors and distillation columns without compromising safety.
So the picture here is our group process flow diagram. So let me explain more about it. Cumene is produced through an exothermic alkylation reaction between benzene and propylene in the presence of a catalyst. First, the reactants are preheated in a heat exchanger to improve the reaction rate and energy efficiency. The mixture then enters the reactor where cumene is formed, along with small amount of byproducts such as diisopropylbenzene. The reactor effluent is sent through several distillation columns to separate propane, recover unreacted benzene for recycling, and purify the cumene product. Heavy byproducts are sent to trans-alkylation reactor, where they react with benzene to produce additional cumene, increasing the overall yield and efficiency of the process.
So, in the alkylation reactor, we perform a mass balance analysis to determine the flow of each component during the reaction. The total feed entering the reactor is 928.7 kmol per hour, consisting of propane, benzene, and propylene. We assume 100% conversion of propylene, meaning that all propylene reacts inside the reactor. The main reaction produces cumene, while a small side reaction forms diisopropylbenzene, or we call DIPB. From the calculation, the reactor produces 163.55 kmol per hour of cumene and 11.69 kmol per hour of DIPB, with a total outlet stream of 740 kmol per hour. Next, we perform a mass balance for the non-reactive unit, which is the depropanizer distillation column. The feed stream entering this column is 740 kmol per hour and contains propane, benzene, cumene, and DIPB. The purpose of this column is to remove light gases such as propane from the mixture. From the calculation, the overhead product contains 10.215 kmol per hour of propane, while the bottom stream contains 729.785 kmol per hour of the heavier components, including benzene and cumene. This separation step helps improve the purity of the downstream product. An energy balance was also performed for the alkylation reactor. The calculation was carried out using a reference state of 25 degrees Celsius and 50 atm, assuming steady state conditions and negligible kinetic and potential energy changes. Using the heat of formation method, the overall enthalpy change was calculated to be negative 5,229.81 kilojoules per second. This negative value indicates that the reaction is exothermic, meaning that heat is released during the reaction. Therefore, proper temperature control is required to maintain safe and stable reactor operation. Finally, an energy balance was performed for the depropanizer distillation column. The analysis assumes steady-state operation with negligible changes in kinetic and potential energy. The reference state used in this calculation is 80 degrees Celsius. Based on the enthalpy difference between the inlet and outlet streams, the heat duty required for this column is approximately 8,598.50 2 kilojoules per mole. This heat is mainly used to support the vaporization and separation process inside the column, allowing process inside the column, allowing propane to be separated from the heavier component.
Moving on to section 3.1, the piping layout or strategies defined by the safe and short principle. We've organized the equipment to minimize the pipe runs, which reduces both material costs and pressure losses. Our layout utilizes a central pipe rack system to streamline the transport of process fluids between major units. We have specified carbon steel A10C for the majority of our piping because of its high tensile strength and ability to withstand the operating temperature of our distillation processes. Additionally, the layout includes dedicated zones for valves and instrumentation to ensure our operators can perform maintenance and emergency shut-off quickly and safely.
We're going to calculate the pressure drop at the fourth pipe, so we need to assume that all the components are incompressible fluid with steady flow, where the mass flow in will equal to mass flow out, and there's no change in velocity, height, and also the work of turbine since there's no turbine in the systems. And these are the information available at the inlet stream of P4. So firstly, since there are two components in the stream, we need to find the average molecular weight before multiplying it with molar flow rate to get mass flow rate. And then we find the volumetric flow rate using density of benzenes, since benzene is the richest component in the streams. Next, we find the velocity using the equation Q equals to VA, and then substitute them to find Reynolds number. And as we can see, the value for Reynolds number is greater than 4,000, so it is a turbulent flow. And then we can find the friction factor and also the friction loss. By using the Bernoulli's equation, we can simplify it to get the pressure drop of P4. And here is the table of summary of pressure drop in another pipeline.
For the strategy in delivering main products in section 3.3, we've implemented an integrated approach to plant reliability. Our delivery strategy utilizes a just-in-time inventory system for hazardous raw material to reduce the risk associated with large-scale on-site storage. To optimize our process, we use numerical methods to solve energy balances, allowing us to adjust flow rates dynamically based on our purity requirements for Cumene and IPA. This strategy ensures that our plant doesn't just meet the production targets, but operates within the highest efficiency and minimal environmental impact, aligning to our technical design and sustainable industrial practices.
Now we're going to calculate the pump power at P10, which is the streams for Cumene production. Firstly, we assume that the pump efficiency is 85%, and the value we obtained earlier, we know that the pressure drop at P10 is 707.1 Pascal. Similarly to the previous one, we need to calculate the mass flow rate, the volumetric flow rate, velocity, Reynolds number, friction factor, and also friction loss. And now using the Bernoulli's equation, we simplified them to find the work of pump, and from there, we just divide it with pump efficiency to get the actual pump work. And finally, we just multiply it with mass flow rate to obtain the pump power. To design the storage tank for Cumene, the product flow rate leaving the final distillation column is 163.545 kmol per hour. And using the molecular weight of Cumene, we can roughly get the values for mass flow rate and also the volumetric flow rate. And assuming a storage capacity of 48 hours production and a 20% safety margin, these are the estimated dimension and capacities of the storage tank.
To conclude our video presentation, I will end it with a conclusion. In conclusion, this project shows us how principle of chemical engineering and fluid mechanics work together in designing a chemical plant. Principle of chemical engineering helps us understand the reaction to produce cumene, while fluid mechanics helps us control how the chemical flow through pipes and equipment efficiently. The main lesson we learn is that balance is very important. Engineers must consider both the chemical reaction and the physical limit of the equipment to make sure the plant runs safely and efficiently. Through this project, we use calculation to design a process that saves energy, reduce waste, and ensure safety. It shows that the theories and formula we learn in class can be applied to solve real industrial problems. Overall, this project helps us understand how to design a safe, efficient, and sustainable chemical process. That's all from us. Thank you.